Many real-life systems evolve in ways that are uncertain and dynamic. A stochastic process is a mathematical model that helps us understand how things changes over time when randomness is involved. Today, we explore this powerful idea that lies at the heart of modern probability and statistics. This is Dr. K. Muralidharan, a senior professor of statistics working with Maharaja Sajirao University of Baroda and an adjunct professor with IIT Gandhinagar. Okay, so what is stochastic process means? Any random phenomena which depends on time of its occurrence is called a stochastic process. Therefore, it's also called random process or dynamic process, which changes according to time. In many real-life situations, if you see, they are all attributed to probabilistic or random phenomena by default. So the time can be anything like seconds, minutes, day, week, month, and so on. Let's see some examples. So the marks obtained by students in an examination, the income of a group of people, outcome of tossing of a coins, etc., etc. So here you can see that most of the time they are random. However, they may not be stochastic processes. They're independent also, they are identically distributed also. So because of this property in IID setup, so they are not stochastic process. They are random, purely random process. So look at these examples, growth of populations. It changes according to time. Fluctuation of current due to thermal noise is again changing according to time. So look at all these examples detailed there. So somewhere some connection with the time of its occurrence is natural. So all are random variables because dynamic in nature and not identically distributed. This is very, very important. They are not identically distributed. So the distribution changes from interval to interval, time to time. And so they are not independent, hence they are all stochastic processes. So that is the difference between IID and non-IID cases. So let's see understand some technical facts. So the notation generally we use xt suffix or x of t. So where t belongs to some time space. So xt is called the state space and t, capital T is called the time space or index space of the process. So it can be discrete, time can be continuous as well. So if it's discrete, time is discrete, we may say discrete stochastic process, and if it is continuous, we may say continuous stochastic process. At the same time, state space can also be discrete or continuous. So based on this, there is a classification of stochastic process. So discrete time, discrete state space, discrete time, space, continuous state space, like that. So examples are also shown there. So you can see how the changes affects the state of happening of anything. So if both the time space and the state space are discrete, we may bring into Markov chain concept. So altogether it's a discrete. So Markov chain concept is actually a discrete time, discrete stochastic process type of. Now, yes, if time is continuous, we may say continuous time stochastic process. So otherwise, discrete time space and continuous state space, we may say discrete time stochastic process. So, so this dependent structure is very, very important in all stochastic processes because the variables are not independent; they depend on each other. So let us say two random variables x and y. So it's a very general theory. So probability of xy can be written as p of xy or px given y into p of conditionally and marginally, it's a multiplication of that, and it's extended for three variables and extended for n variables. So you can see how that can be written. So if they are identically distributed and independent, then you could have directly written probability of x1, x2, etc., xn as simply probability of x1 into probability of x2, etc., probability of xn. So that's kind of things cannot happen if it is dependent. Okay. So the property of dependence is very, very important to learn stochastic process. Okay, so the whole analysis in the dependent structure is totally different from the IID setup base. So to facilitate that, to shorten the study, you can make use of the Markov property concepts. So let us understand what Markov chain, then we'll understand the Markov property aligned with that. So suppose xt is a stochastic process defined for various values of t. So the Markov property assumes that the dependence of xn does not extend beyond the immediate predecessor xn minus 1. So that means, so for a given value of xt, the value of xs where t is less than s does not depend on the values of x of u, that is where u less than t. So in simple sense, it says that if given the present, future is independent of the past. So any process satisfying this property is called Markov process. And a process for which both state space and time space are discrete is called Markov chain. So the whole idea of Markov chain is coming through the dependence property. Okay, so let us see Markov property in a technical format. So you have a distribution, say, random weights process variables x1, x2, etc. xn. So you have probability of xt n equal to xn. Given all those, can be seen that it depends only on the, suppose xtn is the future event, then it depends only on the current event, that is xtn minus 1, which is equal to xn minus 1. So it's the dependency on the past event is completely gone. So in short, probability of xn given xn minus 1, etc., x2, x1 is equal to simply probability of xn given xn minus 1. So a stochastic process for which the above statement is valid is a Markov process. Okay, let's see some applications first. So you can see natural and physical science, a lot of application, physics, chemistry, biology, ecology, and environmental science. A lot of things, depends. The phenomena, the random phenomena are coming through a dependency of with respect to time of its occurrence. Population dynamics, if you say epidemiology, genetics, okay, Brownian motion, diffusion process, they are itself stochastic process applications actually. So noise modeling, etc. So medicine and health sciences, many often people use live testing and reliability concepts or survival analysis based concepts. So you are modeling time to events rather the actual state of the happening. So pharmacokinetics, epidemic modeling. So there are many, I mean, the big applications of stochastic process. So many often you can encounter discrete based stochastic process, continuous time based and continuous state space based stochastic process. Statistics and mathematical science, of course, very huge applications you can see. Time series modeling itself is a very big concept of stochastic process, where ARIMA modeling, moving average techniques, moving average and ARIMA model combined, you can use SERIMA models. So all these econometric based applications, many often you can see stochastic process. So Markov chain concept itself. So Monte Carlo simulation is one of the most powerful simulation method where you generate samples based on dependent samples based on some probability distributions. So that's the whole idea of generating samples is nothing but Monte Carlo simulation. Engineering technology, of course, is another wide area of where stochastic process is widely used. Communications and signal processing, queuing system, reliability engineering, control systems, we use stochastic process applications. Of course, finance and economy, stock price modeling. So most of the time, the variations, the volatility indices, etc., you can bring into stochastic dynamics, and you can understand and the pattern of ups and downs uh, regarding a particular stocks, etc. Investment rate models, risk management. So these are various applications. Okay, so the applications are plenty, therefore Markov chain concepts and Markov chain process is also very important. So please do watch my next video that is on Markov chain concepts on the channel Elucidation and Interpretation. Thank you very much.